Today we're going to be working on nth roots, which means it's more than just square roots. We can now move up to cube roots, fourth roots, fifth roots, and so forth and so on. So our warm-up here is just to get us used to square roots once again and just the process of what's happening. So the square root of 81 is 9, and that is because 9 times 9 gives us 81. So since there's two of those, that's the square root. It's 9 squared. Square root of 64 then would be 8. The square root of 9x squared would be 3x. The square root of 12x, that one doesn't have a nice square root, but we break it down, we pull out the number pairs, and anything is not that doesn't have a pair stays inside the x. And for the last one here, we have two pairs of y's that would come out and nothing would remain behind. The only other thing with square roots is you have to be careful because, for instance, if you put a star next to number 3 here and take a look at that more specifically, the square root of 9x squared is not always just 3x. You have to be very careful because what happens if x equals negative 2? So you take the square root of 9 times negative 2 squared. Well, negative 2 squared, that's a positive 4. 9 times 4 is 36, and the square root of that is 6. But if x equals negative 2, we would have gotten negative 6 out for our root. So the way we counteracted that and made sure that we are getting the correct answer is you have to have an absolute value, but not all the time. Only when you have an even degree inside and you take out an odd degree on the outside. Okay, so that's one of those rules that kind of gets forgotten all the time. An even degree going to an odd degree outside of your radical, you needed the absolute value to make sure that you get the correct answer. And we'll talk more about that later in the video. So let's take a look at how the exponent plays with the root here. So we know this first one, 5 squared is 25. 5 times 5 is 25. So 5 is going to be a square root of 25. Now, you don't normally see that 2 on the outside there. If you have the square root, there is an implied 2 here. Okay? Versus this next one here, 4 to the third is 64. That means 1, 2, 3. If I multiply 4 times 4 times 4, I get 64 back out. So in order to undo that, because 4 cubed is 64, we can take the cube root of 64, and there's now a group of 3 4s giving us 4 back out. So likewise then 2 to the fifth, 1, 2, 3, 4, 5. If I multiply all those out, I get 32. I guess those goes here though. So therefore 2 is a fifth root of 32. So 32 goes under the root symbol with the 5 on the outside, and that equals 2. So when we're looking at all of these, now we're kind of changing up our different number on the outside. That number on the outside is known as your index. So that tells you which root you're looking for or how many in a group you need to bring that out. Your radical symbol just means that we are looking at, the opposite of an exponent. It's a radical. The number underneath the radical symbol, that is known as your radicand. And whatever it equals, whatever you get back out, that is known as your root. So we are able to then take square roots, cube roots, fourth roots, fifth roots, and all of those different types of roots. Sometimes we do get positives and negatives back out, but sometimes, like number 3 in our warm-up, we have to be careful because we don't always get positives and negatives back out. So you can mess around with where your negative sign is. If the negative sign is on the outside, the negative square root of 16 means it's the negative of 4, so it's negative 4. With cube roots, you could have that negative sign on the inside because negative 3 cubed gives us 27, so the cubed root would be negative 3. You also can mess around with the plus or minus. So it's saying plus or minus, then take the fourth root of 16. So if you want to, what you can do is you can break down 16 if you don't know it on the top of your head. And you're looking for a group of 4 within there. So this would be plus or minus 2, because 2 to the fourth is 16. But sometimes we can't take the square roots of negative. So for instance, the square root of negative 16 or the fourth root of negative 16, these will not work. So this chart here is trying to design to figure out which roots are real and which roots aren't real. So for instance, if you have an even index, so if you have the square root, the fourth root, the sixth root, and if the number inside is greater than 0, so this would be a positive number inside there, you're going to get a real solution. And not only that, you'll get one real solution that's positive, and you'll get one real solution that's negative. Let's take a look at the solving example. We would square root both sides and get plus or minus the square root of 5. So we got one positive root and one negative root. Well, what happens if we keep on going with the square root, the fourth root, and the sixth root, but you have a negative number inside? So negative something is inside there. Well, when we try to take the square root of a negative number, that's not a real solution. So we end up with complex roots. And if it's a square root, we could do that, but we can't do the fourth root of a negative or the sixth root of a negative. So if you have a negative inside and you're taking an even index, you get 0 real solutions. So you can actually write no real solution. And the last case with this even index is taking a root of 0. So the square root of 0, the fourth root of 0, the sixth root of 0, you're always going to get 0 back out as your root. But then we move over to the odd indexes. So we're talking cube root, fifth root, seventh root, etc. So if you take the cube root of both sides here, you get one solution, x equals 2. And since it's a positive number inside, you got a positive number as your solution. Now you do get only one real solution. You would also get 2 imaginary solutions for this. Whereas this next one, if you take the cubed root of negative 8 for this, you would get x equals negative 2, meaning that you do get a negative answer back out. So you can take the cubed root of a negative. And this last one, cubed root of 0, fifth root of 0, all of those always gives you 0 back out as your answer. So let's go ahead and take a look at some degrees. If you have these memorized, the ones that aren't shaded out, if you have these memorized, it goes a lot faster when you are simplifying radicals. So go ahead, pause the video, and fill out all of the white boxes and don't fill in the shaded boxes. So now that we all have these perfect cubes, squares, fourth root, or to the fourth power, to the fifth power, etc., these numbers are going to be the ones that are nice to cube root or fourth root or fifth root. So these ones, you should kind of have this familiarity with it. So if I ever asked you, for instance, the cubed root of 64, you can just know that that would be 4, because 4 to the third power is 64. So our first few examples down here are going to involve nice radicals. So there's no issues here, like all of these numbers are on our charts. So the square root of 16 is 4. X to the 8th, our index here is telling us we're looking for groups of 2. So if you imagine 8 of these being written out and pairing them up, you can see that there would be 4 pairs you would bring out. So for this next one, the negative sign out in front is totally fine. We have x squared minus 6 to the 8th, and there's no way we want to multiply that all out. So instead what we're going to do is we're going to view x squared minus 6 and just pretend that we have 8 of them. Once again, we're looking for pairs, so there would be 4 pairs of x squared minus 6's. So we can leave our answer like that. We do not want to multiply those all out. For the next one here, 243, if that one's not really like right on top of your head right now, you can take and break this down, and you are looking for groups of 5. The index on the outside is telling you how many you need in a group. So as we're looking at this, we can see we have a group of 5 threes, which means 3 to the 5th power is 243. So we bring out a group of 3s. If we have 20 A's, imagine writing out 20 A's and then circling groups of 5. We will end up with 4 groups in total. Now for B to the 25th, imagine writing that out 25 times and then circling groups of 5. You will end up with 5 groups in total. Now for these ones, you'll soon notice that you can divide your degree by your index to get your answer in terms of how many groups you will have. So now let's look at the 4th root of y to the 4th. For that one, you have 4 y's and you want a group of 4 of them, so you bring out your y. For number 8 here, the square root of this is going to be imaginary. So we know the square root of -1 is I. So when that's the case, you can write down no real solution, because for these ones, we are looking for your real solutions only. For this next one, we're looking for a group of 6. So again, if you need to break it down, you absolutely can do that. And you'll find that we do have a group of 6 2's. So we can bring that out. And then we have x squared minus 3, 18 times over. So if we circle groups of 6 in there, we end up with 3 groups in total. Now I haven't circled my answers for example 7 and example 9, and it's because of this last question here. When do you use the absolute value symbol? Well, the problems that we had arose from the 4th root of negatives, the 6th root of negatives, the square root of negatives. So you're going to use the absolute value only when you have an even index, because otherwise we can take the cubed root of a negative. The other thing that has to happen is that you have it to have an even degree on the inside. Because if you had an odd degree and you did like -2 to the 3rd power, you would have a negative on the inside and you couldn't do the problem in the first place. So if you have an even degree, it makes it so that you can do the problem. But then when you get your answer here, you have to have an odd degree on the outside that would give you normally a negative number, but we can't get a negative answer with those. So that's when you use your absolute value. So if you look at number 7, you can see it fits all the criteria. I have an even index, I have an even degree on the inside, and I took out an odd degree on the outside, so I need my absolute values for that one. Same thing with number 9 here, even index, even degree, simplifying to the odd degree means that I need the absolute value around that term there. So let's take a look at now just a couple more of these examples. So for instance, example 10 here, the square root of 36y to the 6th. The square root of 36 is 6. If I have 6 y's and I'm grouping them in pairs, I'm taking out 3, but even degree, even index, odd answer means that that would be an absolute value. So go ahead and pause the video and try numbers 11 through 15 for those ones. So using your index as your number in a group, you can see your answers for 11 through 15, and only 2 of these required absolute values. That was 11 and 13 because they followed the even to an odd pattern. We will go over the rest of the not nice answers in a separate video here. So go ahead and log on to that next video. Thanks.